Here's pre-calc. This is problem 7-130. It's about a plane that is flying with an airspeed of 540 miles per hour, and it's in the direction of 45 degrees east of north, and it encounters a wind that is blowing in the direction of 78 degrees east of south. So 78 degrees east of south, if this is south, this angle is 78. So I went ahead and drew in a kind of an x-axis right here. And because 78 plus 12 equals 90, I'm going to just call this angle -12. And then this magnitude's 47. This picture is very hard, and these aren't degrees. This picture is very hard to look at. But the reason I included it is because it wants to know the true speed and direction of the plane. So we know the wind is blowing, the wind's kind of helping the plane along, but it's also kind of blowing it down, so it's going to probably close this angle up a little bit. But if I actually add these vectors up, just, you know how we add them from head to, or initial point to terminal point like that. If I add those up, I can get the true speed and direction of the plane. So basically you're going to add vectors. Even if you don't really know how to draw the picture, you can add vectors if you get them into component form. So the easier way to, instead of looking at this mess, I'm just going to draw each vector separately. So here's my vector that had the 50, I stopped putting, it's not degrees. Oh, it's 540, sorry. This is my 540 vector, and the 45, and I have a x and a y, so I want the component form here. So I can just use my SOHCAHTOAs, you know, cosine is adjacent over hypotenuse, so cosine of 45 is x over 540. So then if I multiply both sides by 540, I have 540 cosine 45. That's going to give me component form. It's going to give me this side of the triangle, which is my x. And then do the same thing here, but use sine, and I got y. So now I have, that's called component form right there. If I can get the other vector, the wind vector, into component form, I can just simply add the x's to the x's and the y's to the y's. So for the wind vector, I just drew it. Remember how it was going down by 12? So, and its hypotenuse was 47. Here's the original picture of it. I went ahead and did 47. I didn't even show it, did I? Oh, I showed it right here. 47 cosine -12 and 47 sine -12 to get the side, you know, the x and y coordinates, so I can have the components of the vector. And so now I have the components of the plane vector and the wind vector, and I just kind of stacked them up right here and added them. So when I add those up on my calculator, I get this. Okay, so that is actually the component form for the true speed and direction of the plane, but I need to put it into like polar form. I need to put it into, I need a magnitude and direction for that vector. So here's, I just rewrote the component form here, and I'm going to go ahead and draw out the triangle. So if its x component was, you know, that number, and then the y is that number, I can figure out the magnitude just by using opposite over adjacent. That's tangent. So I'm going to use tangent because I need to find the angle measure. So tangent of theta is opposite over adjacent. So I inverse tangent both sides, and I find out that theta is 41.01, which kind of makes sense, you know, given our original diagram and the way the wind was blowing. All right, so, but the angle, when we're doing navigation, we don't want to give the angle like we usually do in math. Normally in math, we open up our angles from the positive x-axis, but in navigation, we want to talk about its relation to true north. So it needs to be given with respect to due north. So if that's north, like this is how we like angles to be in math. We like to open from this horizontal axis here. And that's 41, but if I want to open the angle up from the north, that's going to be just 90 minus 41. And that turns out to be 48.99, and that's east of north. Okay, now I didn't give the magnitude yet, so I can just use Pythagorean theorem. You can pause this video too if I'm going too fast. So I'm just going to take the sides of my triangle, like a squared plus b squared equals c squared. That's what I did here. And I found the true speed was 566.97. Right, and this was 41.01. Okay, that's the answer for letter A. Now, letter B says, oh boy, letter B says, how long will it take the plane to travel 1,000 miles in the resultant direction? Resultant, by the way, means the answer to an addition problem. So, what we can do is just, you know how distance equals rate, distance equals rate times time. So if we want to go 1,000, that's going to be the rate. Remember the rate that we just found? The rate we just found was 566.97 times time. And if I want to know what time is, I divide both sides by 566.97 and I get 1.76 hours. So that is the answer for letter B. And then letter C is the most confusing part. It says if the pilot intended to fly 1,000 miles in the direction, the original direction of 45 degrees north of east, how far from his intended destination is he given the situation in part B? Well, I think the situation in part B is that the wind hit his plane. The wind affected his plane. He did just want to go whoop like that, but the wind is kind of like, it's making him go a little faster. The wind's giving him some extra speed, but it's also changing his direction. So if we want to know the difference, because doesn't it say the difference? Well, maybe it doesn't say the difference, but it says how far from his intended destination is he, given the situation in part B, which is the wind. So I think what we need to do is find the intended direction. So if he originally wanted to go 1,000 miles in the 45 degree direction. So I just found the like component form. Like I found that this ends up being 707.11 because I just did cosine and sine on it to solve for these. And that gives me component form of the intended direction. And then I'm going to remember that other triangle where this was like the wind, was the resultant after we took the wind into consideration. And remember we found out it was 427, remember right here, these two sides. I'm going to multiply these two sides by, remember we found out the time? Didn't we find out the time? Yeah, it was 1.76. So I multiply, that's what this is. I multiplied it by the time to see what this distance is. This distance is rate times time, and to see what this distance is. So now I have, this is like a vector form, the component form of the actual direction. because of the wind. Okay, so now I have the intended direction and the actual, and now I just want to find the difference. So the difference, I just subtracted this one from this one. And I actually did it the wrong way the first time, and it still turned out fine because we're going to use Pythagorean theorem on it. I actually, you know, subtracted the wrong, like put the other one on top. It would still work though. So this is the difference vector, and I'm just going to fix this up, and because I need it to have a magnitude and a direction, not just a component form. So actually, I don't even care about the direction. They just want to know how far. So really, I just need the magnitude. I'm not going to bother with the direction because I think we already have that. But so I just put it in Pythagorean theorem, right? Because a squared plus b squared is c squared, and I got 69.57 miles. I think I'm about out of time on this video.